don't know that. I'll check whether that is a minus or it is an equal sign. Because you're talking of 4.1, yes, times 15 upon 9.81, which is equals 26 times 15 by 9.81 minus 4.1 times 15 upon 9.81, and that translates to 33.5 kilograms per meter per kg. For that, horsepower developed in our case will be equal to work done per second by 750, which is 33.5 by 10 by 9.81, and that gives us 4.38 horsepower. We still have another example for you to have a look at, where for a Pelton wheel, tests were carried out and the following results were obtained. Head at the base of the nozzle was 12.5 meters. Yes. And the discharge of the nozzle is 400 liters per second. Jet diameter 10 centimeters. Horsepower developed to 600. Horsepower loss in mechanical resistance was 15. Then determine horsepower loss in the nozzle and horsepower in the hydraulic resistance in the runner. And in the case of turbines, and you please note that power developed equals to rho GQH times eta. For turbines, you multiply by eta, you don't divide by eta, or the efficiency. Okay? Otherwise, horsepower equals to rho GQH times eta divided by 750. Velocity of the nozzle equals to, you're looking for the horsepower in the nozzle. Velocity of the jet equals to Q by A, which is 4Q by pi d squared, which is equal to 0.4 by pi by 0.1 squared. And that translates to 50.9 meters per second. Therefore, velocity head in this case, I think the ABCs are misplaced. Velocity head V squared equals to velocity head V squared upon 2G equals to 50.9 squared by 2G, which is 2 times 9.81, to give 132.05 meters. In this case, loss of head in the nozzle equals to head at the base of the nozzle minus velocity head, which is 125 minus 132, and that becomes minus 6.9 meters. In this case, you neglect the negative loss of head in the nozzle. So therefore, horsepower loss in the nozzle equals to rho GQH eta by 750 is 1000 by 9.81 by 0.4 by 6.95 by 1. Unless otherwise stated, you take 1 for efficiency, divide by 750, and this translates to that 6.36 horsepower. Now, B horsepower loss in the runner in hydraulic resistance equals to horsepower available at the base of the nozzle. Okay? Which should be equal to horsepower developed plus horsepower lost in the nozzle plus horsepower lost in mechanical resistance. But we know that horsepower available at the base of the nozzle is rho GQH by eta by 750, which translates to 1000 by 9.81 by 0.4 by 125 by 1 by 750. That is 654 horsepower. Therefore, horsepower loss in the runner in hydraulic resistance is equal to 654 minus 600 plus 36.636 plus 15, and that remains you, or that leaves you with 2.64 horsepower. So you look at this when we share the notes, and you can try this at your own time. Where a Pelton wheel has a head of 60 meters, out of which 1/3 is lost. Is the lost? I think I need to frame that again. Or is the lost, or it's lost in the penstock. The mean bucket velocity is 10 meters per second, and the nozzle discharges 1 cubic meter per second. If the buckets have an angle of 15 degrees, I think that needs to be edited. At the outlet and the CV 0.98, find the horsepower of the wheel. That is part 1, and part 2, hydraulic efficiency of the Pelton wheel. I'll check where I got this one from. I write it nicely so that you can be able to give it a try at your own time. Then another one is here. Design a Pelton wheel using the following data. Head 200 meters, horsepower developed 1000, speed 300 RPM. Assume another relevant information. Number 3, design a Pelton wheel using the following data. That's another question. Head is 300 meters, horsepower developed 1000, speed is 200 RPM. Find the jet diameter, bucket size, and the number of buckets required if the efficiency is 85% and CV 0.98. Assume another relevant information. That marks the end of that. What we'll do is that I'll run a tutorial on this. We solve some of these design problems. Who knows? KenGen may take some of you. Though there isn't much to do in KenGen, but they need civil engineers. So we run a tutorial through this, and we see how we can be able to design for a Pelton wheel. Otherwise, I will also share these notes with Victor Desmond Tutu. You go through them before we can have a tutorial, and before we can have a cut. Okay. I have that for the Pelton wheel, dear all of us. Please find this. Okay. So I'm sharing for the Pelton wheel turbine. So having seen that, ladies and gentlemen, the next one we'll see, or the next one we shall have a look at is the Francis turbine. We'll have a look at the Francis turbine. All this for the Francis turbine. Don't be scared of the main diagrams. We shall have a look at this and see how we can go about its design. Okay? And then last but not the least, we shall look at the Kaplan turbine. Anyone with a hot question? Any question?
I have a question.
Yes.
What's the difference between total head and manometric head?
Hey, that's a way. I think you should tell me.
No, I see in the formulas you are using total head.
I'm using total head for the turbines or for the pumps? Have you asked that with regard to turbines because we are doing turbines? Or you are,
For turbines, use total head.
Or you are asking that with regard to pumps?
Generally.
Generally.
Yes.
Is it? Massimumbi. Now, when you talk of manometric head, it can also be translated to be the total head developed by the pump. Okay? Yeah. Though I told you in practice, remember I use the word in practice. In practice, what they would call manometric head, I will not regard it as such. That is theory. That is theoretical. The reality is you take the delivery head plus all the friction losses, okay? Plus what I called, you can remember, residual head. You remember that? Can you remember me mentioning residual head? Anyway, manometric, we can say it is the total head, okay? Or else we can say it will actually represent the difference in total head between the pump's outlet and inlet, okay? That is, if you consider things like pressure head, velocity, and the suction. But the thing is, the manometric head is the head against which the pump has to work. Because I told you, the pump does nothing to lift water from the sump to where the impellers are. You remember that? So out in practice, if you want to, you can use manometric head. Nobody will judge you harshly for that. But you'll be wise if you use delivery head plus elevation head plus, sorry, if you use elevation head plus friction losses plus what I'm calling residual head, which we normally take as 10 meters. Okay? That is if you're working for Davis and short leaves. Sawa. I hope I'm not confusing you. Mercy? Speak up, Mercy. Hello? Mercy umeenda wapi? Mercy Mumbi, I'm talking to you. Nani anamuona karibu? Hello? Is Mase Mumbi there? Sasa unauliza swali ndo unanyamaza. Huh? Anyway, hata ukinyamaza, it is taken at the total head, developed by the pump, and it is the energy to add to the fluid. That is in theory. Okay? It is also the same amount of head which we are calling the manometric head, which is imparted by the impeller to the water. Okay? Or else you can say that manometric head is the total head at the outlet of the pump, or the total head at the inlet of the pump, or minus the total head at the inlet of the pump. But I told you the pump does nothing to raise water from the sump to where the impellers are. Otherwise, I would consider from the pump to where you are delivering that water at the total head you are pumping against plus the residual head. The residual head, you use it as a safety measure so that you do not under design. Okay? So whoever has heard me can tell Masi Mumbi that. Okay? Another question. Another question. Nyamboke, any question? Boke.
No question.
Collins, any question?
No question.
Okay. Then we shall have a tutorial on what we have done. And others, when we have done them, we'll do a lot of calculations so that you can be conversant with these things. Otherwise, when it comes to the pumps, don't mix up or don't get mixed up with what we are calling manometric head. Some people say it is the total head. Fine, it is still the total head. And it is HD plus HS plus all the other losses. But I would say it is HD plus HFD plus VD squared by 2G. Plus, that is me. Plus, what I'll call residual head. That is what I'll do in practice. And when you do that in practice, you'll never go wrong. You'll always get it right. Okay? Many engineers don't know that, but that is what you do in practice. Okay? If someone decides to put together suction head and elevation and delivery head, and he says that is the total pumping, fine. You are not losing anything. The only thing I told you is that when you are installing a pump, never get it wrong when it comes to the installation of the suction pipe. Okay? Look at the altitude so that based on atmospheric pressure, you can make a decision on the correct HS. And you know how to compute for HS. If need be, factor in the Toma cavitation number by dividing whatever you've gotten as your HS with the Toma cavitation number. That way you'll be able to avoid a situation where the pump will encounter what we call cavitation. Sawa sawa. but we are talking about turbines. Okay? So if you have no more questions, ladies and gentlemen, agreed with Desmond, we meet on Thursday from 9 o'clock for 2 hours. So from there, we shall chat our way forward. See when we can do a cut. I will also bring back your, I will have worked on your graph. Some of you drew them badly. I don't know why. And you had the freedom of doing them the correct way. Under no threat, under no duress. But I'll still bring that. It is an assignment, but I'm here to give you a cut. Unasikia George Lundi? George, unasikia?
Yes.
Hey, utaangalia kama yako ulichora vibaya ndio uniambie kwa nini. Anyway, thank you so much, ladies and gentlemen. Enjoy your evening. Take care. Read your notes properly. They will tell you everything. And if you have any questions, don't shy away. Just ask. We shall discuss fully what you are looking for. Bye-bye for now. Enjoy your evening. Bye.